In this video, we're going to look at intermolecular forces. Intermolecular forces are forces of attraction or repulsion which act between neighboring atoms, molecules, or ions. We can contrast intermolecular forces to intramolecular forces. Intramolecular forces are forces within a molecule, such as a covalent bond. Therefore, the substantial difference between intramolecular forces within and intermolecular forces between is whether the force is holding the molecule together or if the force is attracting or repulsing molecules in the bulk. Intermolecular forces have two characteristics. One, they determine bulk properties, boiling point, melting point, similar bulk physical properties. They are also electrostatic in nature. As an electrostatic attraction or repulsion, intermolecular forces decrease as distance increases. It's one of the reasons that in gases, when atoms, molecules are very far apart, we can say that the attraction forces between them are very low. There are several different types of intermolecular forces. There are ion-ion interactions. These can also be considered ionic bonds, or also intramolecular forces. We're not going to discuss that in detail in this video. There are ion-dipole interactions. These usually occur in mixtures or solutions. Hydrogen bonding, dipole-dipole interactions, and London dispersion forces. We're going to focus on these last three: hydrogen bonding, dipole-dipole interactions, and London dispersion forces. If we look at hydrogen bonding is the attraction between the lone pair of an electronegative atom and a hydrogen atom that is bonded to either nitrogen, oxygen, or fluorine. Let's look at water, H2O. If we think about what's going on in the molecule, we have an electronegative atom, oxygen, that's pulling electron density towards itself, giving us two bond dipoles. These two bond dipoles are going to give us a partially negative and a partially positive charge. Here's where we get our electrostatic attractions. Then we will set up an interaction between the lone pair of the oxygen and the hydrogen. Hydrogen bonding interactions are very strong. They're very strong because the hydrogen is very small, meaning that the lone pair of the nitrogen, oxygen, or fluorine is very close in distance. If we consider our next intermolecular force, dipole-dipole interactions. Dipole-dipole interactions are electrostatic between permanent dipoles in molecules. If we consider the molecule hydrogen chloride, again, like in water, we're going to have a dipole moment going towards the more electronegative atom. This is going to set up a partial negative on my chlorine and a partial positive on my hydrogen. That will give us an electrostatic attraction between the chlorine and the hydrogen. Not as strong as hydrogen bonding, but still a significant intermolecular force. The last intermolecular force, London dispersion forces, are sometimes loosely called Vann Der Waals forces, are forces that are very weak. London dispersion forces are weak interactions caused by temporary fluctuations in the electron distributions within nonpolar molecules that create instantaneous dipole moments. We have to remember that the electrons are not static around a molecule. They're flowing in an electron cloud. And as such, it's possible for the electrons to end up on one side of the molecule or the other. Let's consider bromine. Bromine is a very electronegative atom. It likes to have a high electron density. So if we consider two bromine atoms, Br2 and Br2, normally they are nonpolar. But if any one time we end up with a little bit more electron density on one side of the bromine than the other, we can end up with a partial negative and a partial positive. This partial negative and this partial positive can actually cause an induced instantaneous dipole in an adjacent bromine. Once we have this instantaneous dipole and this induced dipole, we can have a London dispersion force or an intermolecular force between these. Of course, this is instantaneous dipole. So then as soon as that occurs, it could balance back out and be gone again in another instant. So London dispersion forces are very weak. They only happen for a brief amount of time. Let's consider a problem and how we might apply intermolecular forces to physical properties. Rank the following molecules in order of increasing boiling point, low boiling point to high boiling point. We have fluoromethane, methanol, and ethane. To figure out which of these has the highest boiling point, we need to think about which of them has the strongest intermolecular forces. If we think about kinetic molecular theory, we're going to need to have enough energy in our system to overcome the intermolecular force. So the substances that have the greatest intermolecular force will be the ones with the highest boiling point, the ones where we have to put the most energy. Let's draw these three with their geometric structures. So here we have fluoromethane. If we think about fluoromethane, it's a tetrahedral. We have a bond dipole towards the fluorine. We also have very small dipoles towards the carbon. So if we consider the fluoromethane, we have a dipole between the carbon and the fluorine, and that's going to set up a molecular dipole towards the fluorine. That means that this can have a dipole-dipole interaction. If we look at the methanol, here again we have dipoles going towards the oxygen, but we also have a hydrogen attached to an oxygen. This is a key that we have the possibility of hydrogen bonding. So anytime we see an oxygen, nitrogen, or fluorine, we need to be looking for a hydrogen. Because it has hydrogen and free lone pairs on our oxygen, this can do hydrogen bonding. In the last one, we notice here all we have is carbon and hydrogen. Carbon and hydrogen have a very small difference in electronegativity. These bonds would be considered nonpolar. I have nothing in here that would be considered a polar bond. Since the entire compound is nonpolar, the only interaction that we can have here is not ionic-ionic, not dipole-dipole or hydrogen bonding, but just London dispersion forces. Therefore, if we think about these three, which one has the strongest intermolecular interaction? Well, that's going to be the hydrogen bonding. Well, which one has the second? That's going to be the dipole moment. And then finally, the London dispersion forces. So if we rank these, we'll see that we can have the ethane is going to be the lowest boiling point, fluoromethane greater than that, and then methanol will have the most. Now, the problem didn't say to look up the values, but we can look up the values for these, and we'll see that we get a boiling point of minus 89 degrees Celsius, minus 78.2 degrees Celsius, and 64.7 degrees Celsius. This is pretty common, where you'll see hydrogen bonding having a much higher boiling point or melting point than other substances of similar mass. Intermolecular forces are very important. It turns out that hydrogen bonding is essential to DNA and how it works. Dipole moments are also important to recognize so that we'll know what types of interactions are occurring and what type of reactions can be occurring. Practice determining intermolecular forces and become confident.